Okay, so welcome to lecture 16, part 1. We're going to be starting chapter 4, section 2. It is a big section. It's very dense. It contains a lot of information. So we are just going to do the first bit in this video. We're looking, oops, I should not abbreviate until I've introduced the subject. We're looking at precipitation reactions. Okay, there are lots of different kinds of reactions, and they can be subcategorized, subclassified, and precipitation reactions are one of those classes of reactions. Precipitation is what happens when something leaves solution. Okay. So if you have, for example, a double displacement reaction, a precipitation reaction, you can, have two solutions, A, B, C, D. You mix them together in a bigger thing, you'll end up with, for example, CB still in solution, and a pile of solid AD down on the bottom of the beaker. So that's precipitation. The solid AD comes out of solution. For example, silver chloride. It's insoluble. It comes out of solution. Another example is just rain. Okay? Rain is water that has been dissolved in the air, and it will occasionally find something to nucleate around, or maybe the temperature drops or what have you, and that dissolved water will fall out of solution as liquid water. So, really quickly, a solution can be unsaturated. Let's see, it's an E. Go ahead and make that clear. That's a U, so it can be unsaturated. It can be saturated, or it can be super saturated. So if it's unsaturated, that means that it has less than 100% of the maximum amount that can be dissolved. Okay? If it is saturated, then it is at 100%. And if it is supersaturated, then you guessed it, it has more than 100%. And yes, that is possible. It's what's known as a metastable configuration, meaning that it will exist until some disturbance comes along. And then, it will precipitate and leave you with a saturated solution. And that disturbance can be a change in temperature. It can be the addition of a crystal of the solid that will precipitate. In some cases, if you set it up really, really well, it can be, just a loud noise. A clap is enough of a disturbance. And then you'll just get solid coming out of solution, and you'll have a saturated solution left behind. All right, so that's what you get for precipitation. Just something coming out of solution, leaving you with a saturated solution of the precipitate. Now, the reason I'm going through all this is because looking at precipitation reactions, you are going to have to be able to predict whether there's going to be a reaction or not. So let's talk about solubility. Any potential solute, remember, solute is the thing, dissolved. Okay, so any potential solute can be soluble or insoluble. Now, you might think that soluble means it will dissolve and insoluble means it won't. And you would be wrong. Okay, soluble means a lot dissolves before saturation. Insoluble means tiny amount dissolves before saturation. So, sodium chloride is soluble in water. Okay, we're talking about things being able to dissolve in water here. Sodium chloride is readily soluble in water. Let's see. Ethanol, ETOH, is perfectly, in fact, soluble in water. Sodium chloride, you can throw in just handfuls of salt before it'll stop dissolving. Ethanol, it's perfectly soluble. It'll never stop dissolving. Eventually, instead of having a solution of ethanol in water, you'll have a solution of water in ethanol. Okay, I mean, it's just, they never stop. There's no point where they separate. All right, insoluble compounds, that's where, it's very, very tiny, minuscule, not insignificant, but very tiny fraction is soluble. So silver chloride is insoluble in water. Barium sulfate is insoluble in water. Calcium carbonate is insoluble in water. Now this is limestone. Okay, the fact that it is insoluble in water is why limestone exists. It forms a lot of land masses and so on. The White Cliffs of Dover, Florida, the Carlsbad Caverns, but it's not entirely insoluble. It's not perfectly insoluble. A small amount of calcium carbonate can dissolve in water. And, tiny bits dissolving in water and then getting left behind as water drips from the ceiling of a cave onto the floor of a cave is why you get stalactites and stalagmites. Okay, some will get left behind up here as the water drips off, and some will stay here as it dries from the floor of the cavern. All right. So that's soluble and insoluble. What are the solubility rules? Because you need to know the rules if you're going to predict whether or not a precipitation reaction can occur. Now, some things are always soluble. You have a salt made with one of these ions, it will always dissolve no matter what. Okay? So the alkali metals. Okay, so that would be the first column in the periodic table, the first group. So sodium, lithium, potassium, and so on. Also, always soluble are some polyatomic ions. So C2H3O2 1-, that's the acetate anion. Also NH4+, that's ammonium. And then we have nitrate, NO3 1-. And chlorate, ClO3 1-. Okay, so those are always soluble. You see one of those in a salt, it will always dissolve, in large quantities before it hits saturation. Now, we have usually soluble. They are fluoride, the other halides, so Cl-, Br-, and I-. Fluoride is a halide, but it has slightly different behavior, so we can go ahead and separate that out. And finally, sulfate, SO4 2-. So these are usually soluble, except with, for fluoride, it is the alkaline earth metals. So that would be calcium, barium, strontium, magnesium, things like that. Lead 2+, and iron 3+. Okay. So fluoride is going to be soluble, say sodium fluoride or titanium fluoride, but not if it's with an alkaline earth metal, lead 2+, or iron 3+. So magnesium fluoride, lead 2 fluoride, I should say, or iron 3 fluoride. Okay, now the halides, they will be soluble except with silver, mercury 1, and lead 2+. So yes, that is a polyatomic ion there, the Hg2 2+. So For example, mercury 1 chloride would be insoluble, so that would be Hg2Cl2 would be insoluble, it'd be a solid. But mercury 2 chloride, HgCl2, would be soluble. Okay? Just one of the quirks of the universe. So sulfate is generally soluble, except with the heavy alkaline earth metals. So that would be barium, calcium, and strontium. And with silver 1 plus, lead 2 plus, and mercury 1. So let's go ahead and draw some lines. Let's try and make it easier. Okay. All right. So those are the elements that are usually soluble, but not always. You are pretty much going to have to memorize these. Fortunately, the always soluble are easy to remember, and there's kind of trends, like lead 2 plus, rarely soluble. Okay, silver, rarely soluble. The alkaline earth tends not to be soluble. So it's not the most impossible thing in the world to remember these. Let's go on to the insoluble compounds. So always insoluble. We have carbonate, chromate, let's see, sulfide, phosphate, and then a separate group, OH minus. Now, these are always insoluble, except with the always soluble. Okay? So if something is always soluble, that overrides the insoluble rule. So, for example, sodium carbonate is going to be soluble. Okay, carbonate tends to be insoluble. Sodium is always soluble. So the solubility of the always solubles wins. So sodium is too happy to go underwater. All right. Now there is an addition. So this for hydroxide. So hydroxide is always insoluble except with the always soluble and barium. Kind of random, but you know, what you gonna do? You know, sometimes the universe is unkind. All right, those are our solubility rules. Try and keep those in mind. Your book has a handy table for you to refer to, and there are also charts you can Google. I'm undecided as to whether or not I will provide you with a table of solubility rules on the test. I think I probably will. I might get mean toward the time of the test. So, let's look at some examples of precipitation reactions. This is my abbreviation for precipitate, so I also use it as my abbreviation for precipitation. So, what you're looking for with a precipitation reaction is an insoluble product. If you have one, then you have a reaction, and you can write down a net ionic equation. If you don't have an insoluble product, then no reaction, and that's all you write. You don't have to, there's nothing to balance. There's no reaction, no equation. So, for example, one I've already showed you, sodium chloride plus silver nitrate goes to form what? Well, they swap partners, so sodium is going to go with the nitrate, and silver is going to go with chloride. So sodium nitrate, you look at your solubility rules, Sodium is always soluble, nitrate is always soluble. That's a double whammy. Soluble. Silver plus chloride is one of our insolubles. So, silver chloride, solid. If you were to reduce this to a net ionic equation, that's Ag plus Cl minus goes to form solid silver chloride. Now let's go ahead and try magnesium sulfate plus barium hydroxide. Okay, sulfate tends to be soluble. Barium is one of the exceptions for hydroxide, so it is soluble. Hydroxides tend to be insoluble. Barium's the exception. That's what I'm trying to say. So they would swap partners, leaving you with magnesium hydroxide and barium sulfate. Oops, that's a 2. All right. Now, are these going to be soluble, insoluble? What? Well, hydroxides are insoluble, except with the always soluble, or barium. Magnesium is not an always soluble, so this will be an insoluble solid. Sulfate is generally soluble, except with, for example, barium. So it is also an insoluble solid, meaning this is a god-awful mess. No dice. Well, I mean, there is going to be a reaction, but it's going to be a reaction that you'll regret. What we tend to like with precipitation reactions is one insoluble product, because that's easy to collect. 2 insoluble products, you'd have to find some way to separate them, and that's not always easy. Let's go with another example, one that's a little bit kinder. Let's go with sodium carbonate and calcium nitrate. So when you mix those together, you're going to get sodium nitrate. Notice that you still have to balance these. Okay, so 2, 2, 2 plus calcium carbonate. Well, sodium and nitrate are always soluble, so AQ. Carbonate is always insoluble, except with the always soluble. And calcium is not one of the always soluble, so you're going to get limestone falling out of solution. All right, let's go with ammonium chloride, aqueous, and potassium acetate, C2H3O2, aqueous. You mix those up, and what do you get? You get potassium chloride plus ammonium acetate. And let's look at our solubility rules. Potassium is an alkali metal. Chlorine, or chloride I should say, is a halide. Potassium is always soluble. Chloride is almost always soluble. It hasn't encountered one of its exceptions, so this is aqueous. And then both ammonium and acetate are also amongst our always soluble, so this is likewise aqueous. So what we have right here is no reaction. All right, and that's enough examples of that. I think we'll go ahead and call it a day. When we come back, we will continue our discussion of various kinds of reactions.